Okay, welcome to the week 10 lecture video on sequencers. So this is the PowerPoint. You can download the PowerPoint and then you can click the link right here that says week 10 video, and basically that will launch you into what you're watching right now. So you must have did that. But here's what we got going on. You would go ahead and write your name on the attendance sheet, pass back your lab 8 and your homework 8. Should have been passed back to you, I'm sorry. You should have that. Collect homework 9 and lab 9. Want to make a little note that the labs are getting a little more theoretical. Last week I asked you to really pay attention and read the textbook and understand what's going on, and it seems like the class is doing pretty good on that. But we're really dealing with a lot of number systems, especially the binary number system, and that is super critical to you understanding how the PLC works. So let's start with our last week review. We had some issues with the data type, and so that goes back to a Boolean, which is true or false, versus a dent, a double word, for example. You can't address a contact because a contact can only be opened or closed with a dent, because a dent has 2 billion different number combinations that it could be. So when you're moving data around, you want to be sure that you are identifying the data type, whether it's an int, a dent, or a Boolean. Okay, and then when it says data type mismatch, when you compile it and then you click on the link to see where that's taking you, that's really what that means. Is that somewhere in your rung of ladder logic, you're trying to mash those items together. Okay, and it doesn't work. And part of this is just with experimenting and learning like normal, getting your hands on the control logic software and seeing how it all works. So we're doing okay there. Okay, so what we did for the lab review, we took 1, 1, 1, 2, 2, 2, 3, 3, 3. These were numbers that were already predetermined, and then they were loaded and unloaded into a FIFO first in, first out. And we're going to really examine this to be sure that you understood how it went. You're supposed to be watching the data stream when this was working. Okay. So on the lab review, the FIFO unload, first in, first out, and first in, first out, load and unload are the FIFO word shift. Okay. So we had array 0, and then we had a length of 10 here. Okay. So how many words do we have? Well, we had 9, because that first position 0 is not used. Okay, so you learn there that if you wanted to do the RPM and have 5 items, you had to make your length 6. Okay, so that was the first thing that people figured out. The FIFO array, then you took a look at that, and that held all of the data, and we will once again take a look at that a little bit. But we were loading and unloading first in, first out. We weren't doing last in, first out, or last in, last out. We were just taking the first word in, the first word out. So if you looked at the ladder logic, it was important for you to understand that in order to unload right here, you had to have this rung true, because this rung isn't necessarily true. To either unload with your enable button or to do a manual unload, you had to have this true. How did this rung get true? Well, this bit had to get true over here. And how did this bit get true? Well, when the FIFO control was done, it turned on, and we got a little memory going on right there, and it locked in. How does the FIFO control get done? Well, when the position reaches the length, then it gets done, and this came done for one scan real quick, and it got locked in, and then this was true, and at that point we could unload. So basically, when we were first pushing this button for the first 9 times, all we could do was load the array. We were unable to unload the array because the unload instruction had not been activated yet. Okay, so here's a FIFO example video. So you would like to stop the video here for a minute and then click on this link. It's a little bit long, but I want to be sure that you understand how the FIFO example video, how that all works. Okay. All right, so we're back, and here is what the lab looks like. So it looks like we pushed load 3, which first in right here was 3333, because that's what load 3. Then we did load 2, load 1. So we got 222, 111. And then we did 321 again. So here's 321. and then we did a 1, 3, 2, 1, 3, 2. Now, there you go, 1, 2, 3, 4, 5, 6, 7, 8, 9. So the first 9, all this did was load up the array, at which point we got that done bit to come on, which allowed us to not only load it, continue to load it, but then to unload it every time we push the button. So when we finally got around to unloading it, the first thing that got unloaded was a 333 right here. What number is that? It's this one right here, because this was the first one that we put into the array, and therefore it is the first one out, because we did first in, first out. Okay? If we did last in, last out, something like that, it had been this one here, but we did first in, first out. And then we did push it again in this 2, 2, 2, and then we push this in 1, 1, 1. But now be aware that even though we're unloading it, we got to load 1 here. We push this 3 out, but we then did stack a 1, 1, 1, 1 back down here because everything was shifting up. And just as this 2, 2, 2 went out, well, yeah, we did put another 2, 2, 2 back in. And this, if we put another 2, 2, 2 back in, and then this 1, 1, 1, 1 would have went out. So we continued to load the array even as we were unloading it. And so 3, 2, 1, because it was 3, 2, 1, 3, 2, 1, because it was 3, 2, 1, 1, 2, 3. So it followed this order here. Okay? And then when we were all done, we could manually unload it. So we just click unload, and everything here would just get up, 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 and it'd be gone, at which point then the done bit went false, and we could start again. Okay? So on the engine RPM, we once again mentioned that if you want 5 cycles, you would have had to made it 6. And so basically you were kind of loading, and then you started unloading. Many of you did. So that data was gone. The 6, the 7, the first 5 were gone as you went to 6, 7, 8, 9, whatever. And then at the end of a minute, it stopped until you had 5 values in there. Okay, so we unloaded all the ones up to that point. We had the 5 values in there. And then what we did was we manually unloaded those as we had shown previously. Okay, we got a little worksheet here, so we'll pause the video and let's take a look at this video. So pull up PowerPoint and click this link right here, data activities 1 and 2, and we will do those. Okay, you should take a look at this. Hope you understand the way the words are shifting. The next one we have here in the lab was the bit shift. And so we were talking about the length between the word and the bit shift array. So this bit shift array, some of you were making it 14, some of you were making it 24, 32, whatever. We had this array and we were putting a number of bits into there. Okay, but the thing that controlled it was the control right here, the bit shift control, and we made that a length of 14. Okay, and just like on the words, the length of the control dictates how much data we actually keep into, that we continue, that we can modify and move back and forth. Okay, so the way this works, it looks like part present. This is either going to be on or off, and then so we got data going into here, a 1 or a 0, depending on this light is on or off. So this was kind of what we were doing, and we were pushing 1s and 0s into here depending on the status of this light. Okay, and that seemed to go well. So what I have right here is just a little review of the bit shift, and this is a little bit of a longer video, but I wanted to be sure you understand. When you're shifting left and right on a SLC 500, the word is vertical, and when you're shifting up and down on control logic, it's up and down. So the word moves in a different direction. Sometimes it's a little bit confusing. So go ahead and you'll pause the video and go ahead and click this link here, this bit shift example link. Okay, we're back. So now we have another bit shift example here, and let's do one in class. So go ahead and grab this worksheet, and here's we're going to take a look at the ladder here, and go ahead and pause this, and then go ahead and run the video right here. Click this link for the video, and let's do this worksheet in class together. Okay, we're back from there. We had the rework activity on the lab at the very bottom, and basically what that was doing was we were taking a failed part. And so if we had to take a part off the system that I showed you, we basically hit the input, and if there was a 1 in there, we put a 0 in there because we unlatched it. Unlatching, it'll put a 0 in there. So we took the part off the system, in this case, I guess at station 7. And then we advanced the array keeps advancing. But when that 0 went down the line, when that 0 got to 8, we said, hey, there's an opening on the line. We want to put the part back on. So we push this button right here, and we are able to put a part back in the line. Okay, and then so the line would have all 1s in it. Hopefully we're all making all good parts, 1, 1, 1s. But if we had a bad part, we put a 0 in there to indicate that we didn't have it, and then we pushed a 1 back in. Now here I'm using, I got a failed part, and I got a move with a mask here. Okay. And what we're going to do is we're going to talk a little bit about what masking is, okay? So what we've got is a couple of things right here. Move with mask. So this is just not a move. This is a masked move, okay? So in this case, we're using, this is showing bits because this is Slick 500, but we're basically moving data from B3, it looks like, into B34, so 30 and 34. And we're using this mask right here to dictate how much of it we keep and how much of it we don't want to keep, okay? So if we were to look in this file right here, this would probably be a dent, okay, this bit, and it would have a bunch of 1s and 0s right here. So this is what we are moving, okay? So this is the new data, okay? But what we have is a mask right here, FFOF. Well, if you understand your hexadecimal and all this kind of stuff, you can take this FFOF, and you know that F is 1111, 0 is 000, F 111111. So this is our mask, okay? So the way that this works is if there is a 1 in here on the mask, then we're going to take the new data and we're going to overwrite the old data with the new data, okay? So if there's a 0 in here, we're going to take the new data and we're going to disregard the new data and we're going to keep the old data, okay? So here's the new data, here's the old data. So because these all have 1s in them, that means we're going to take all this new data, 10101, and we're going to overwrite this data here with the new data, okay? This data, this is the old data right here, 1100. But because the mask is 0, we're going to keep that old data. So the 1100 just comes straight down. And then this here, we look at the mask, this is 1111. So we are going to get rid of the old data, 1100, and put in the new data, 1010. So that's how the masking works, okay? So what we have here is the bit shift rework with mask. So it looks like we were trying to, on a failed part, we're going to move some numbers around, and what we were doing here with this mask is 1024, and I think that's what when the worksheet asks. And so what I want to show you is when you're working with a mask like this and you have 1024 and you're like, it's probably got something to do with bits 9 and 10 here or something, I'm guessing, okay? And so what I like to do is I like to have a tag called mask or masker, okay? And so the value that we just had there was 1024. Well, what do? I'm going to change this to binary. Excuse me, I'm going to change this to decimal. And I'm going to put in 1024 and hit enter. And then I'm going to change this back to binary. And it shows me that there's 8, there's 0, 7, 8, 9, 10. It looks like this involves something with passing data, allowing data to pass, because that's a 1, into that bit right there. So if you take a look at the move with mask, this basically says because these are 0s, and I've got a 1 there, that's talking about I've identified that bit location of where I want those things to go to get moved. So remember when you're doing the mask, if you have 0s and data is going to stay the same. And then otherwise, with ones, you're going to take the new data. We will do quite a bit of masking a little bit later. Okay, but let's take a look at the data activities 3 and 4. And you can stop the video right now and click on the masking example video right here, and let's take a look at some masking. Okay, we're back to the lecture, and just want to talk about the purpose of the control for the bit and the word shift applications, and also for the sequencer. So the control, remember what that does, is that's where we're putting in I guess the number of steps, whether it was 14 or it was 6 on the data acquisition, etc. But when we put in the control, this gives us a lot of bits right here. These are predefined. Our done bits is one of the ones that we were using, or our unload bit and our enable bit, stuff like that. So that's what the control does, is when you then schedule that instruction and you give it a control, there are specific bits now related to that instruction that we can use in the ladder logic. Okay. So our homework review. Basically, we went over that sequencers are used when a repeatable operating pattern is required. And so an example that I saw was, I believe, L&W Engineering. I was looking at one of their work cells. And this work cell did, let's say it did 65 steps. Okay. And in step 1, it had 2 outputs on. So we would have a sequencer with a word, if you can imagine, it would have 00001, 00001, 00 whatever. So 2 ones. And those ones turned on specific outputs, which might be like the robot interlock to tell the robot to start moving, and maybe turn on a conveyor. And then what it did is it jumped to the next sequencer, the next step. And in those 2 ones that were there before, well, they went to zeros. So that means the robot interlock went low and the conveyor stopped. And then it had, let's say, 3 ones came on. And those 3 ones were cylinders. So maybe a couple, 3 cylinders came on and held the part. And then the sequencer went on to the next step. Maybe 2 of those cylinders stayed on, so we had a couple of those ones. And then maybe 2 other ones came on at different locations, which were the sealer gun and maybe the drill press or the drill or something. So that's the way that this went through. And so you could see this on the HMI, that they just showed the sequence of the word. So it wasn't a very exciting HMI. All it had was a bunch of registers, double words with zeros and ones. The next one 0 to 1, next one 0 to 1. So that when the item actually failed and they had to try and figure out why it wasn't working, well, they could just look at the screen, and it showed what step of the sequencer it was on, which word on the control, and then they could see which items were supposed to be on. They could also look at the inputs and see which inputs were supposed to be on, and then that's how they troubleshot from there. And what this did is this didn't allow the operator to actually get into the PLC. They didn't have to have a computer, and they didn't have to look into the PLC at all, so they couldn't mess it up. All they had to do was look at the HMI, and the HMI replicated the status of the control words. Pretty interesting, huh? Think about it as we work on things today. Homework review. A group of outputs can be controlled by a single instructions as compared to using a number of PLC discrete outputs. That's what we're going to be working on, is controlling groups of outputs. Okay. So our group homework, we were talking about doing some Christmas lights. So if you'll pause right here, and we'll take a look at the group homework video by clicking on that link right there, and we'll do the group homework together. Review quiz. You had a quiz that will be reviewed, so you can take a look at that. The next is the sequencer and shift register instructions. That's what this chapter is about. Okay. So mechanical sequencers. Once upon a time, they didn't have nearly fancy PLCs, and they used mechanical sequencers. And what these did is, this is an item that turns, okay, and it's like a car engine that's got cams and lobes on it. And this first wheel's got a little higher lobe, and this one's got another higher lobe. And so when these lobes roll around, they activate switches. And so they they make a 360-degree turn, and then the cycle starts again. Maybe this one was initially on for a few seconds and off, and this one was off and on and on and off. So it was, like I said, very similar to your automotive engine. Okay. What I also equate these to is a music box. So when you wind it up and the music box turns and then it plays music because the little springs are clicking on the wheel. It's really neat to see those. And then the song plays and then it goes all the way around and the song starts over again. So here's a cam operated sequencer. They got the cams, they got high points on them, and this spins at a certain rate. Could spin 1 revolution per minute or 1 revolution per second or whatever. And that at different times these high points activate switches and they close and things turn on and off as this thing rotates around. Hopefully you understood that concept from the book. Here is a drum. These little red things indicate pegs. So as this rotates around, it looks like this output right here, or this input would go on, then off, then on, then off, 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 all the way. I'm going the wrong way, sorry. On, then off, then all the way off, 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 until it came back around. Okay? And so this is what I was talking about with like a music box. That these are the little springs on a music box, and this thing just spins and it plays music. In this case, this spins, and each peg is represented by an on or off. So we can take this as an input, or we can take a look at an output table. That's what we'll be doing, is putting zeros and ones into an output table. Okay. A washing machine is a good example of that, because your washing machine fills it up with water when this is hit, or I guess it's drained, and then you fill it with water, and then you turn on the washing part, and then you drain it out, and you turn on heaters, and then as that goes around, as this thing spins, it starts the cycle again, or it may cause it to rinse again or drain again, then rinse again and drain again, and then pretty soon it makes 360 degrees, and then that means that your cycle is done. So a washing machine is a good example of a timed sequencer as it kind of rolls around and completes the cycle. So what we're doing is our sequencer instructions. They're going to be under File Shift, and the ones we'll be using is sequencer. Up here, we'll talk about sequencer load, and there's some other ones here involved, but this is the same menu where we had our first in, first out, and all our file operations. Okay, that's where they are. So we have our sequencer output, and what that does is it pushes words to an output module, and then that's what we've been talking about a little bit, and I'll show you my Christmas lights here in a little bit. Sequencer load. That means that you can load up a file using sequencer load. We're not necessarily using that. And then here's your compare. You can compare different bits on different words. So those are some of the sequencer ones. Okay. So here's your sequencer output. Your file is your is what is going to have the words in it. So it's going to have your 10111101s. The next is going to have a different batch of zeros and ones. The next word's going to have different zeros and ones. Okay. The mask is a bit pattern through which they're moved. We already did the masking. So if you just want everything to come through straight away, then your mask is just going to be, 111111, which is FFFFF. So you came here and you wanted to make this your mask -1. If I looked at my mask as a hexadecimal, that made everything FFFs, which if I looked at a binary is 11111s. So if you make your mask like that, then the word and the data comes through perfectly without any changes. Okay. Versus if you make your mask 0 and things get modified. Okay. Destination is the output word. So if you're taking this destination, you might just store it somewhere, or a lot of times we're pushing it to an output module. Okay. The control, that's your enable bit, your done bit, and your parameters that we talked about. The control, it says the length is the number of steps of the sequencer starting at position 1. Okay. Position 0 is the startup position, so that you got to remember that we kind of lose the position there. Okay. And so here's what it looks like on a SLC 500, and here's what it looks like on a Control Logics. Our array would be our SQO file, and our mask is masker. If I throw masker of all ones in there, then it's not going to make too much of a mess. And we're taking this to output lights. We're going to data, okay? And then our control right there gives us our bits and our length of 34. So apparently this is going to hold 34, 33 words, different words in here that are going to get pushed out to the output module. Okay, so to program a sequencer, binary information is first entered into the file. Okay, so you've got a file and you got to populate it with zeros and ones. Okay, so if I were to come here and I was going to look at this first one here, I've got storage array is what my sequencer array is. So if I come to storage array, what am I looking here for? Storage array, there it is. So if I came into my storage array, this, I guess I would have to make this a little bit bigger. Oh, I've got 70 on it, I do. So this is where you would load up your information that you want to pass out to here. And another part here, I've got another one called SQ file, and that is one that I've started to load up here. I've got SQ file, and so I put the number in here. These are the numbers that get moved around. These are the words I want. So what does this mean? A lot of times, you know, you might want to look at it as binary. If you push it to an output module, this would be off, this would be on, then off and off, then on, then off, then on and on. So, but a lot of times you want the relationship between decimal and binary. Okay, so going back here, those zeros and ones could be shown as binary, hexadecimal, or decimal, whatever, as long as you convert it and you know what they're doing, what you want them to do. And it advances through the step. It starts here with zeros, and then it goes to step 1, 1, 0, 0, 0, 1, and then it advances to this step, this step, this step, and then it would start over again. Okay, just like that washing machine rolls around from beginning to end, this would go all the way down, and it would start up again if you kept indexing that sequencer. Here is a sequencer used to control traffic in 2 directions. So what you have is an output word. It looks like you push all zeros in here. Nothing's going to happen. But then at step 1, it looks like you turn it on output 0 and output 5. So output 0 would be the red light here in the one direction, and you would want green in the east-west direction. So you wouldn't want 2 green lights, because then the cars would run into each other. So, and then it goes to the next step, which it looks like it's got on 0 and 4. So 0 and then 4 red, and then it puts a yellow light here. You go from green to yellow so that these people will slow down. And then finally it puts in 3 and 2, because now they switch directions and go the other way. So this is an example of a sequencer, and then this just jumps to the top and starts over again, over and over and over again, and as cars go through. So here's a sequencer used to control that. It's going to have the file, which is the order of events here, the zeros and ones. The file is this word, this word, this word, and these control the lights. It's going to have a mask. It looks like the mask is, we've got ones right here, because we are changing these bits, 0, 1, 2, 3, 4, and 5 bits. We got zeros all the way here because we don't want anything going into here anyway, so we just masked it out, so it's not really part of the equation anymore. So the mask allows the new word to replace the old word. Okay, that's what those ones do. And then our control, they've got it, R6, this is shown a length of 4. Step 1, 2, 3, 4. Here's that 5th position that we talked about. That's the default or start position. So length of 4, and it'd be position 1. Okay. The sequencer requires a preceding logic on the run to go true. So when this goes PB1, this advances its position, which then moves to the next word. And then you push it again, and it moves to the next word, and it cycles through the words right here every time this comes true, when it goes from false to true. Got some different sequencer programs here. Sequencer programs can be event-driven, or they can be time-driven. Okay, so an event-driven would be that, you know, a mechanical limit switch causes that sequencer to go. But a popular one is to be time-driven. So if you wanted the sequencer to change every second, you could put it on a timer done bit, and then that timer keeps getting done, done, done. So if you want to look at a time-driven sequence, let's see what I got here. This looks like a time-driven sequence. So basically, this timer starts right away, and it times to a second, opens, resets, opens, resets. So this timer keeps resetting. But what this timer then does is every time it gets done, it's going to go here, and it's going to take my array, and it's going to run through my masker, and it's going to push the number out to the HMI. What number is it going to push out to the HMI? Well, it just depends. It looks like I've got a length of 8, so it's got 8 different numbers that it pushes out to the HMI, and then it will go back up, and it will start over again. Okay, so I'm looking for my storage array here. Let's see if I can find it. Did I not populate this one? So the first one could be, it would push that out, and then it might push this out to the HMI, then it would push this number out to the HMI, and then it would push this number out to the HMI. Oops, I guess I could take larger numbers. I could populate all these numbers to go out to the HMI, but remember, after a certain point, when I exceed my my file, when I get down here, if I put some numbers in here, these won't get pushed out to the HMI because my length is only 8. Okay, so I'm only looking at the numbers here that fall within the length of the file. Okay, and that's time driven. And so here's the sequencer chart. List the sequencer operations, and if it was time driven, it looks like the first time I'd have lights bits 0 and 7 on. Next time I'd have lights 1 and 6 on. Then I'd have lights 2 and 5 on, and 3 and 4 on, whatever. And this is what I was talking about with L&W Engineering, how they kind of put this data right here on the screen so that you saw what was supposed to be on and what step of the sequence you were on, but you actually couldn't get into the PLC to do anything about it, and at least you kind of maybe knew what was wrong. All right, so let's take a look at the Christmas lights, and we're going to see if we can kind of see some stuff shifting here a little bit. So if I come here and I come back to here, let's look at this Christmas light. So these are the dancing candy canes that I've been doing lately. And so they go kind of back and forth, and these are running on a Slick 500. And you see how the candy canes go back and forth. I think there's about 14 outputs on here. We'll have to check them in a minute. And you can see that the candy canes run some sequence. Okay, so I quit out of here, and I look at the candy cane. Oh, it's going to be this one here. If I look at the candy cane program, it looks like this. So this is going to be true. So I got a timer that this timer looks like it counts to 0.15 seconds because that's my time base. Okay, and so it keeps getting done, done, done. So this gets done, 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 done. Keeps blinking every 0.15. So what does it do? It takes my file, which is right here, and it takes my mask right there, and it pushes out to my output module 0, because it's a fixed PLC. Okay, and I've got 200 different items on here, and what is getting pushed out to the lights? Well, if I go and I look at, I'm looking at B3 binary, is that right? So here you go. Look here, it looks like that was my mask. It looks like the lights go, they're going, each step looks like they're going right to left and left to right, and then as they come down here, right to left, and that's kind of what the lights were doing, right? And then farther on down here, I think I've got some lights where they cross or something. No, still going right to left. See the ones there? There's right to left. It's a pretty long file. Goes back and forth a few times. Here they all turn on, then off, then on, then off, then on. And so this sequence of words gets pushed out to the output module. This one gets pushed out, and then this one gets pushed out to turn them all off. And this one gets pushed off to turn these two on. Oh, here's where they cross. This crosses this way, and this crosses this way. All right? So basically, I'm just pushing a word out to the output module each time, causing the lights to blink in a certain order that I want. Okay? So that's an example of sequencer doing the Christmas lights video. So if you want to have a constant time intervals, that's where you have the timer right here. It looks like it's 1 second, getting done, done, done. So you're going to shift through these words every 1 second, and then your output module is going to change states every 1 second. Now, when you have a time-driven sequence where they're not the same, okay, and I want you to listen carefully to this because it's not green for 1 second, yellow for 1 second, red for 1 second, or whatever. There's all different times in here, and that's a problem. There's two different ways to do it. You could get this word. So let's say I'm going to make this a very simple word where this is 0, and this is 0, and this is 1. Let's say we want the green on. 1, 0, 0. All right. So if I wanted the green to be on, what I could do is I could still time this every 1 second. You with me? Every 1 second. So I'd have to push 1, 0, 0, and then after 1 second, I would go to the next word, which would be 1, 0, 0. After 1 second, go to the next word, 1, 0, 0. I'd have to do that 25 times to make for that 25 seconds of 1, 0, 0. So my words. So when I look at that file, I'm going to have, right away, I'm going to have 25 words in that file of 1, 0, 0 to start off. Now, on the 26th step, I could push in the word 0, 1, 0. So for steps 26, 27, 28, 29, and 30, I'd have to push in 0, 1, 0 like that. Okay? And then I could move on to the red. So that's one way to take care of it, okay? To do something like that. Another way to do it would be to use two sequencers. So the way that this works is we have the sequencer right here that's pushing out to the traffic lights, and so the lights are, when the word moves, this moves. This is in the textbook, so you want to take a look at it. It pushes out to the output module, and the timer, every time the timer blinks, done. It looks like that's what happens. But now what this does, it's also got a second sequencer. And what this sequencer does is it changes the preset of the timer. So not only do we get, let's say we get the red light to come on here. Let's say we've got some file that says turn on the red light. But we push in a preset that says run this timer for 25 seconds. So we don't have to have 25 words blinking every 1 second to keep that light red or whatever. We just do it once, and then after 25 seconds, this blinks and it turns on the green light. And let's say the green light stays on for 5 seconds or whatever. Not only does it turn the green light on, it pushes a new preset into the timer of 5 seconds, and therefore it stays on for 5 seconds and then blinks. Okay, so this is two sequencers, one controlling the output, and one is controlling the time base for the timer. Okay, so that's kind of slick there. Check it out, it's in the book. My event-driven sequencer, like we said, switch 1 or 2 will advance this sequencer. So an event-driven, we'd have a destination here with a mask, so the file would move through. It looks like they're not using these middle items here, so they've masked them out. These lights here are not being used, so they've just masked them out with zeros. But otherwise, this word switches every time switch 1 or switch 2 are hit. Okay. The sequencer input instruction. So what we're going to do is we are going to use this, and what this is, it's going to come true when the sequencer is equal, when it's compared against data stored. So what we're going to do is we're going to take in a file and we're going to compare it to another file, and if they're equal, then it becomes true. Okay, so what we do in this lab is we have a sequencer input that's going to come true, and if this is true, it will pass logic, and then it will take a look and see if this one is true, or it will activate this one, which will switch the position, which will make this one false. Okay, what do I mean by that? I think that's this part right here. So what we're doing is we're going to take the HMI storage in right here. Okay, so there's my storage. If for some reason my storage right here matches the input file, okay, my array is input file. Let me close this up. So if I go up to input file and I were to populate that, let's say I put a 123. I'm putting numbers in here for the input file, like a combination for 123. All right. So for some reason, the HMI, you typed 123 in the HMI, and it moved 123 into storage automatically. If when I push this button, this becomes true, which allows this to be processed. For some reason, if the 123 matches the position 6, which it doesn't, because 6 is going to be some number here, like 456. It doesn't match. If for some reason I move this to position 1, though, if I push the button, I take the number 123. That's my input file. If 123 in my array matches the 123 on the HMI, well then this was true, this was true, and then therefore it will make the sequencer true. And what happens when the sequencer gets true? Well, one thing that happens is it moves it to position 2. And the other thing what it does is it takes my file and it puts it to storage 2, and it looks like storage 2 gets moved to the HMI. Okay, so storage 2, and we had some numbers in there, which I'd have to put some numbers in here. This could move a number out to the HMI. Okay, a couple notes. You cannot directly move destination HMI. You just can't put HMI here. You have to put it into a memory location, and then you use a move from that memory location into your other tag, whether it be the thumb wheel or the HMI. Okay, so that's kind of a little trick one. So take a look at this. It's right out of the book. You want to be sure you're understanding what's happening there. Next, sequencer load instruction used to read a PLC input module. And so that's where it's located when you get to that part of the lab. And there's a combination lock where we're going to be doing some comparisons and stuff. Going back to this, listen carefully. These don't have to be in series like this, or they don't have to be in series like this. If you push this button, and for some reason the input file and the source are the same, then it becomes true. So instead of having a sequencer here, you could have a light here or something, and that light would come on, or you could have a move, or you could have any kind of other instruction. Basically, this doesn't need to be used in series here. And so for your combination lock, you may or may not want these to be in series. Just be aware that this comes true, logic just continues on. We've done that. So here's an instruction program once again. This is what we were talking about, where we were taking a file and input was causing that to be activated, and then if for some reason they matched, we could get an activity to occur. Okay. Oh, I'm sorry. This is sequencer load. So what we're doing is we're taking a file and we're loading up the word into sequencer. We're not necessarily going to be messing too much with automatically loading a word into that, but that's a way that you could load up your sequencer based on information that's coming in. And doesn't that seem similar to that FIFO command where you were taking information in? Okay, and you could actually do that. You could take that FIFO and bring those words in, and then you could even use that file for your sequencer if you wanted to. Okay. So I know there's a lot of information here, very theoretical. Just read the lab very carefully and follow instructions and try and be sure you understand what's happening.